So the question is, the first thing is that nowadays quantum mechanics is quantum field theory. People talk about particle physics, and if you look at particle physicists, they don't do particle physics at all. Well, Feynman path integrals, they give themselves the idea that that's what they're doing, but they're really doing quantum field theory. And so, what is a particle in the context of a quantum field theory? Was part of the problem that was coming up there. And in particular, the difference between Rindler and Minkowski space is that the natural observer, if you will, in Minkowski space is a geodesic observer, somebody with no forces on, just sitting at the same place or something like that. Whereas in Rindler, the natural observer is an accelerated observer. So the difference in quantizations between the two of them have are related to a difference in what the natural observer is in the two cases. And so showing that this Rindler quantization really ties in naturally with an accelerated observer. And therefore what that paper really showed was that an accelerated observer in the Minkowski vacuum state. So what somebody who was standing still would say, there aren't any particles anywhere. We're in the lowest energy state of the system. In order to create a particle, one has to generate some energy, and if your detector starts out in its lowest state, there's no energy around in order to create a particle. So you see nothing. And yet, if you accelerate someone in that, A, you've got a source of the energy, which is the force accelerating. But B, that accelerated observer sees that same state, the same vacuum state, as if it's full of a temperature of particles with a certain temperature. It excites the detector just as though it were excited by a whole bunch of particles. With a certain, in a state with a certain temperature, and that temperature is proportional to the acceleration. The proportionality constant is wicked because in order to get a temperature of about 1 Kelvin, you've got to have an acceleration of about 10 to the 22 centimeters per second squared, which is an extremely large acceleration. So that's why nobody's ever noticed this. So just as Einstein showed that one's notion of time depends on one's velocity, that two observers who have different velocities have different notions of what the same time is, or even how much time has elapsed. And you get things like the twins paradox and so forth. So just like in that case, here an accelerated observer has a very different notion of what a particle is from somebody who's just sitting there and has no forces on him to accelerate him. The two have very different notions of what a particle is. And that's sort of what I showed in that second section of that paper. And that's since then come to be known as the Unruh effect. As one of my colleagues said, Unruh means restless in German, so this was just like Zitterbewegung, that one stole from the German. Use a German term to explain stuff. So similarly, this so-called Unruh effect was using the word restless in German in order to characterize this effect. So it just was a lucky chance that my name happened to be the same as this German word.
So just for a moment there, I just want to focus on acceleration. So Einstein came up with special relativity in 1905.
Right.
It then took him quite a long time to incorporate acceleration into his theory. I think it was only 1916 when he came up with the complete formulation of general relativity.
It wasn't really acceleration. I mean, that was the whole idea of coordinate invariance. Was what he showed, and so you could have an arbitrary coordinate system. I mean, accelerated was just one amongst many, and there was nothing special about an accelerated coordinate system. Whereas in this case, it really is important that you have constant acceleration in order to have the effect.
What is it that's weird about acceleration that causes these paradoxes, these difficulties? Well, not a paradox, but you know, it's weird that someone sat still or moving in an inertial frame should have a certain notion of what a particle is, and then an accelerated observer has a different notion. What is it about acceleration that causes that discrepancy between the two viewpoints?
It's always hard. I mean, there are a number of things. One of them is precisely Einstein's change in time. So from the point of view, the accelerated observer, his velocity is constantly changing. So there's a constant difference between his notion of time and a non-accelerating observer's notion of time. He's got, you know, he has a time that he could extend to the whole of space and so forth, as if it were Newtonian time, although if you have different velocities, you'd have different concepts of time. Here you've got this constantly changing velocity, so a constantly changing notion of time. And that's one of the key features that gives you this different notion of what a particle is. So a particle, I mean, the catchphrase that I developed years, I don't know how many, but years after I had originally done this stuff, was that a particle is what a particle detector detects. So in a particle detector, you start off with a system in its ground state, in its lowest energy state. So in order for it to become excited, it's got to absorb some energy. And one can call, in quantum mechanics, the carriers of energy, one can call them particles. So in order for this detector to be excited, it's got to, you know, absorb some sort of energy. Because of the difference in time, because of the acceleration, the notion of energy for this accelerated observer is a different notion of energy from the notion of energy of a stationary observer. Energy and time are very closely related to each other. And in addition, there's Doppler shifts. So one of the things that you can think about, if you have a detector and you switch it on and switch it off very quickly, it will become excited because of interaction with the field. So if you didn't have any interaction with the electromagnetic field, let's say, it wouldn't become excited. But because there is, just switching it on and switching it off causes it to become excited, as though there were particles there. And these are sort of switching transients. And one of the ways you can explain that is that in the ground state, in the lowest energy state of the electromagnetic field, there are fluctuations in the electric field itself. So the energy is the lowest, but that doesn't mean that the electric field value is equal to zero. It varies from place to place, even in this vacuum state. So this electric field can interact with the detector and causes it to be excited. Now, usually, shortly thereafter, another electric field comes along which basically cancels this one. And so the detector is sort of in this constant state of jumping around, but if you average that out over a long time, you see no effect, and it just stays in its ground state. Here, because of the Doppler shifting, that next little fluctuation that comes around has the wrong frequency and doesn't excite the detector. So the first one, or de-excite the first one came along and excited it, the second one came along and didn't de-excite it. And so over a long time, that leaves a residue. And you need both of those things in order to get this effect. If you only had one or the other, you wouldn't get a thermal spectrum. You wouldn't get it wouldn't act like it was thermal. There would be some excitation over a long time period, but it would, sort of be a bit of a mess. So you need both of those in order to get the effect. One of the problems in the analog systems that we have worked on since then, where you can mimic some of these things in very ordinary kinds of systems, that you could have on your benchtop, is that, for example, the Einstein time dilation, this change in time due to motion, doesn't exist. The time on your lab benchtop is the usual time, the usual Newtonian time. The accelerations are far, far, far too small to give for Einstein's relativity to come into play. So you need both of these things going at the same time in order to get this effect. So it's some combination of the two of them that causes it. But that's sort of the best I've been able to come up with amongst the many times that I've been asked, where does this come from?
So you mentioned a moment ago that we've never noticed this in our daily lives because the accelerations that are involved are so ludicrously high that it wouldn't have any consequences for just everyday life. Are there any experiments that you could set up in order to observe this?
Directly, the closest has been a suggestion by J.S. Bell, the same guy who the Bell inequalities were named for, and Linus, who I think was a postdoc at the time, I'm not positive. And they wrote a paper in the 80s where there's an analogous effect. So the effect that I looked at was with linear acceleration. In other words, you keep accelerating in exactly the same direction. With exactly the same acceleration as seen by, because time changes, you've got to say who is seeing this acceleration, as seen by the thing that's being accelerated. So constant acceleration, always in the same direction. They looked at the situation in which you have constant acceleration, but in a circle, instead of in a straight line. And what they showed was that even in that case, the detector, again, does not remain in its bottom state. It seems as if it is being bombarded by a bunch of particles as well that it absorbs the energy from and gets excited. In that case, it looks approximately thermal, but not exactly thermal. So the temperature in, and then they suggested that in electron storage rings, at that time there was an accelerator called Hera, or a storage ring called Hera in Germany, in which they stuck electrons and they just orbited for hours and hours and hours. And that the acceleration there was high enough so that of the electron going round and round in the circle was high enough that you got temperatures of the order of about 1,000 degrees above Kelvin, above absolute zero. And furthermore, that the excitation, if you could see it at different frequencies, would look approximately thermal, within about 20%. So that's sort of the closest. That's an extremely hard experiment because the way in which your thermometer there turns out to be the spin of the electron. So if in order to have the electron going around in circles, you've got to put it in the magnetic field. It's the magnetic field that bends it into a circle. That same magnetic field then causes one of the spins of the electron pointing in one direction to have a different energy than the other one. So that could be a thermometer. You start off in the lowest energy and then it jumps up into the higher energy state. And there had been an effect noticed already in the 1970s of that if you stuck these electrons into a storage ring, you couldn't get it to have a single polarization. You, for example, wanted it, because that's the lowest energy, it's easiest to put it in the lowest state, and you would want all of your electrons to be in the lowest state. And yet when they ran the experiment, they would find that there were only sort of like 92% of them there. And that 92% can be interpreted as that it's there because that spin is acting like a thermometer, and this approximately thermal state keeps exciting it and leaves some of them in the excited state and some of them in the ground state. The problem is that there's all kinds of other inhomogeneities in the magnetic field and so forth that could also cause this kind of depolarization, and it's hard to disentangle them. Also, in that case, one can't scan the frequency. It turns out that the sensitivity of the thermometer is set by exactly the same magnetic field that sets the acceleration. And so one can't tune the acceleration separately from where the thermometer is sensitive. And it's always sensitive in exactly the same part of the spectrum. So it works, but it's certainly not an ideal measurement kind of situation. So that kind of a direct measurement is still, let's say, waiting to be done.